Hello guys, I welcome to all of you in this video lecture. In today's video lecture, we will define a cauchy sequence in a metric space, and we will also understand this definition with the help of an example. So here is the definition of a cauchy sequence in a metric space. Let small d be a metric on a non-empty set capital X. A sequence xn in the set capital X is said to be Cauchy sequence if for every epsilon greater than 0 there exists a natural number, say n naught, such that whenever n comma m is greater than equal to n naught, then d of xn comma xm is strictly less than epsilon. So this condition, if sequence xn satisfies this condition, then we say this sequence is a Cauchy sequence in metric space x comma d, right? And this definition coincides with the definition of Cauchy sequence in real number system. If we take the metric small d as a usual metric on capital R. So a sequence xn in R is a Cauchy sequence in the sense familiar from elementary analysis if and only if it is Cauchy sequence according to definition first, this one, in the sense of the usual metric on R. So both the definition, that is definition of Cauchy sequence in a real number system, and the definition of Cauchy sequence in a metric space coincide if we take the metric as a usual metric, right? Now here with the help of example we try to understand this concept. So here we have given let capital X is equal to the collection of all continuous functions which are defined on closed interval 0 to 1, right? And d is a function which are defined from x cross x to R such that d of f comma z is equal to, d is defined like this: supremum of mod fx minus gx for all x belongs to closed interval 0 1. So the supremum of this set is equal to df comma z. So with this metric d and the set capital X, x comma d form a metric space. Now we construct a sequence xn where xn is equal to f of nx. So this sequence and fnx is defined like this: fnx is equal to nx upon n plus x for all x belongs to closed interval 0 1, right? And we will prove that this is a Cauchy sequence in the uniform metric space. So with this metric, a non-empty set of all continuous functions which are defined on closed interval 0 1 is known as the uniform metric space, right? So we have that we suppose that m is greater than equal to n, then the difference between these two numbers, that is mx upon m plus x minus nx upon n plus x, we can take multiply this denominator by this numerator and this by this number. So after simplifying this, we get this is equal to m minus n into x square upon this factor into this factor, right? Now because f is a continuous on closed interval ab 0 1, so it assumes its maximum values at some point x naught on closed interval 0 1. So the supremum of mod fmx minus fnx, where x belongs to closed interval 0 1, will be a finite number, But we observe that their difference, that is fmx minus fnx, will be m upon mx upon m plus x minus nx upon m plus n plus x. But we know that this is equal to this value, right? We already simplified this in the previous slide like this here, right? So this is equal to n minus m minus n into x naught square upon m plus x into n plus x, and this will be less than x naught square upon n plus x naught, because function will attain its maximum value at some point in closed interval 0 when, so we say this point is x naught, right? So this will be less than equal to x naught square upon n plus x naught, and this will be obviously less than 1 upon n. And if we take n very large, that is n tends to infinity, n is very large, that case 1 upon n tends to 0. That means when n and m are very large, then this value tends to 0, or we can simply say that f and x and fn is less than epsilon when n and m is greater than some fixed natural number, right? So from here we can say that this sequence f and x is a Cauchy sequence, or this is not only Cauchy but also it is convergent, and it will converges to some function. Suppose if we take the limit point of this sequence fx is equal to x, then we observe that the d of fnx comma fx, and this will be equal to mod fnx minus fx, that is supremum of mod nx upon n plus x minus x, and this is equal to x square upon n plus x will be less than 1 upon n, and this value is also tends to 0 as n tends to infinity. So this value tends to 0 as n tends to infinity. So from here we can say that the sequence f and x is also a uniform is convergent sequence and will converges to fx is equal to x function. So this is all about the Cauchy sequence.